Hi, my name is Noson Yanofsky. We're doing the class is Discrete Structures. We're doing section 5.2, which is elementary probability. Probability theory is the easiest. Well, let me first motivate. Look, probability theory is going to be used in every single class in computer science, and especially in big data, data analysis, deep data, deep learning, all that stuff uses probability and statistics very, very deeply. So we have to know it well. Okay? Let me just tell you, there are basically no rules in this thing. You'll see there's a definition, and then we go back and use the union rule, and that's it. So it's very, very simple. And let me just tell you what our game plan is. You ready? I do not do any of the problems from the book. The book has 5-6 pages worth of problems. You have to read that on your own. Okay? I do all the even number problems from the homework, and then on the homework, from the exercises, and then the homework is the odd number problems. So you have the ability of seeing every single problem done in the book. And I strongly urge you to stop the video right now, read the book, try to do all the problems by yourself. Just use me as an aid when you can't do problems. I got to tell you, you really have to know probability theory, and you really have to get this straight. Okay, so let me just say what probability of an event is the simplest thing in the world. It's equal to number of ways E can happen divided by number of ways anything can happen. Okay. Again, the idea is probability theory is just two counting problems. That's it. That's it. Just two counting problems. So it's fairly straightforward. And we're going to see the counting problems are not very hard. Okay, let me just give you an example. You roll a die, probability of getting an even. You roll a die, so what's the possibilities? There are 6 possibilities of when you roll a die. The probabilities of getting 6 is as follows. So how can you get an even number? 2, 4, or 6. Those are the even numbers divided by what do you get altogether? Maybe I shouldn't have these. 1, 2, 3, 4, 5, 6. Obviously this is a simple case, so the chances of getting even is 3 over 6, or 1 over 2, or 0.5. Right? When you flip a coin, the probability of getting a heads is 1. So you have a heads over either a heads or a tails. So that's 1 over 2. That's it. Okay? A little bit of notation and discussion. The book goes through a little bit of notation and discussion. Capital omega is called the sample space. This is all the things that can happen. Okay? And you have, this is a capital Greek omega. This is a small omega. This is an element of this. The small letter is an element of that. This is called the set of all events, or the sample space. This is called an event, a single event. Okay? And then you have E, a subset of sigma. These are the events that you're looking for. There's a bunch of them, so it's a subset of that. And basically, what you're looking for is the probability of E. E is the events, okay? And the answer is, again, I explained it, but I'm just going to say it now with notation. It's the number of elements in E divided by the number of elements in sigma. Okay? Can't get easier than that. Each outcome is equally likely, so we try that. Okay, great. So let's start problems. That's it. Now we're going to do a little bit more theory, but not that much. Number 2. A letter of the alphabet is selected at random. Okay, so let me just erase and give you some more room. have about it. Now you can do problem 2 and 4 by yourself. Again, I strongly urge you to do it by yourself. Okay, so press pause, do it by yourself, come back and see what we did. 2. A letter of the alphabet is selected at random. What is the probability that it's a vowel? A vowel is A, E, I, O, U. A, E, I, O, U. There are 5 vowels. So the answer is the probability of a vowel is equal to 5 over 26. Okay? And again, we're going to do the same thing. I'm going to leave, I'm not going to put in these numbers usually, but it's 0.1923. Okay, but you're going to have to put in the numbers. I'm going to just set up the numbers and you're going to have to calculate the numbers. Number 4. A five-letter word is selected at random from sigma 5, where sigma is ABC. Repeat exercise 3. Okay, so let's just do this. Number 4. Okay, alphabet is A, B, C. Okay, we are choosing a letter from sigma 5. Sigma 5. Okay, that's 5-letter words from this 3-letter alphabet. Okay, and we know how many elements there are. These are, 3 to the 5th. Okay, and so that's equal to 3 times 3 times 3 times 3 times 3. You can figure that out yourself. Great, now let's do what we're searching for. What is the probability that the letters in the word are distinct? Okay, so A. Okay, probability letters are distinct. That means different. Okay, now, question. How do you choose a 5-letter word such that there's no, in this alphabet, such as there's no repetition? Answer, that's 0 over 3 to the 5th. I don't care what you have in the bottom because 0 over anything is 0, so that's 0. There's no way you're going to get words that are distinct because there's not enough letters to get a 5-letter word. Okay, number B. What is the probability that there are no vowels in the word? A, B, C. A is the only vowel. Okay, so no vowels in the word. Okay, and the answer is, well, you have a 2-letter alphabet there. Let's just make sure I got this right. You have a so you have 2 to the 5th divided by 3 to the 5th. You're randomly choosing a word from this alphabet. You want to know how many have no vowels, so that's 2 to the 5th. That's just B's or C's. You have, that's how many words there are just made up of B's and C's. Okay, and this is equal to 2 over 3 to the 5th power. I have no idea what that's equal to. Neither did I write it down. Great. Number C. What is the probability that the word begins with a vowel? Okay, C. So the word begins with a vowel. The only vowel that could be is an A. Okay, and now you have 5 other letters. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, and so the answer is you have 5 possibilities for this, 5 possibilities for this, 5 possibilities for this, 5 possibilities for this. I don't mind if there's an A in the rest of the word. Okay, and so the answer is 5 to the 4 divided by, you have 3 possibilities, 3 possibilities, 3 possibilities here. So this is 3 to the 4 divided by 5, 3 to the 5. Okay, and so that is equal to 1 over 5. Sorry, 1 over 3. Sorry. Okay, great. Now, a little bit of theory. Okay, so we did 2 and 4. We're going to go on all the way till number 20. So, but we have to do a little bit of theory. Okay, so we're going to erase this and do this. Okay, and the theory is what we just did. Okay, just some ideas about counting that we know already. So let's just do it. Probability of the empty set is equal to 0. If something is impossible, the probability is 0. Okay, so that takes care of this. Okay, next, probability of any event is less than 1 because it's a subset of the set of all possible. So it's always the fraction, and the fraction is always going to be less than 1, less than or equal to 1. Okay, next, probability of E complement. The chances of something not happening, we're going to see this word not again, okay, is 1 minus probability of E. Okay, so whenever you see the word complement or not, you're going to do subtraction. We saw this before, and the idea is, again, you have basically the probability of E complement is equal to the number of elements in E complement divided by all the elements, and this is equal to the number of elements in the entire thing, well, minus the number of elements in there. Okay, and the idea is this picture. This is the probability of E, and this is 1. The idea is, here's this picture, and here's E. You want to know what's the chances of E complement. It's those things in omega, not in E. Well, same thing. We saw that before. Great. Next, probability of E union F okay, in general. Okay, so again, this is the union rule. Again, this is a restatement of the union rule. Okay, this is equal to probability of E plus the probability of F minus, you counted something twice, the probability of E intersect F. Okay, and again, this is that thing. Basically, here's your omega, here's E, here's F. You want to know what's the probability of both? Well, of all of them, well, it's those things in E plus those things in F. 1 second, you counted this twice. You better subtract it. Okay, so that takes care of that. And finally, if E1, E2, E3, EK are pairwise disjoint. Let me just explain to you what that means. Here's your sigma. Here's your big omega. You have a bunch of different events, but there's no overlap. Then probability of E1 union E2 union EK is equal to probability of E1 plus probability of E2 plus probability of E3 plus probability of EK. Okay, it's adding up all the little probabilities. As long as there's no overlap, that's perfectly fine. Okay, just want to write this another way. It's the sum of the probabilities of EI, where I equal 1 to K. Just add them up. Okay. Great. So this is just a restatement of the union rule. We saw about counting. Well, if the top thing, again, probability is just some of the things that could happen. Well, if things could happen in these ways of the union rule, so this is just a restatement of the union rule. Great. Let's do some more problems. again, it's an idea to stop. That's it. We're not doing any more theory in this, for this. We're not doing any more theory for this section. So the rest of the problems, we're going to do 6, 8, 10, 12, etc., etc. So it's an idea to stop the YouTube video, try to do them on your own, and use me as an aid when you're stuck. Okay? Because you really have to learn how to get it by yourself. Number 6. Okay, you ready? Suppose that an experiment leads to events A, B, and C with the following probabilities. Whoops, number 6. Sorry, that was number 7. Number 6. An urn has 3 red and 2 black balls. So you have an urn. That didn't work. Yeah, this is number 6. You have an urn. You have 3 reds and 2 blacks. B, B. Okay. 2 balls are removed at random without replacement. Means you take them out and you don't put them back in. Okay. What is the probability that the 2 balls are both red? Okay, so let's do this. Number 6, both red. Okay. Number 6. Hold on. Okay. What's the chances? You have 6 balls. You have 5 balls, 3 reds and 2 blacks. What's the chances? You're choosing 2 of them. What's the chances all 3 are red? Answer is like this. There are 3 reds. You want to choose 2 of them. You have 5 balls altogether. You want to choose 2 of them. Okay? And now you have to calculate that number. I'm not interested in doing it. You'll do it. But you have to give me the number as a real number. I mean, this I could tell you is 3, and this I don't know what it is. Okay, great. Let's do B. You have, what's the chances of you getting exactly 2 blacks? Well, there are 2 blacks altogether. You want to choose 2 of them. That's equal to 1. And again, you have 5 balls inside. You're choosing 2 of them. You get that. Great. Number C. Let's just read it. Number C. We're number 6C. What's the chances that the 2 balls are different colors? So what does that mean? That means 1 red and 1 black. That's the only 2 colors you can get. So the answer is as follows. There are 3 choose 1 red and 2 blacks. You're choosing 1. Multiply that because you want 1 and 1 divided by 5. Choose 2. Okay, great. Next, number 8. Let's read number 8. Suppose that an experiment leads to events A and B with the following probabilities. Probability of A equals 0.6. Probability of B equals 0.7. Okay. Show that probability of A intersect B. Show that probability of A intersect B is more than or equal to 0.3. Okay, now this is like this is like every single science class. They give you a bunch of information. They're asking you for something, but there's some equation that we know that has to do it. And the equation is as follows. We saw this as the union rule. We just saw this 2 minutes ago. A union B is equal to probability of A plus probability of B minus probability of A intersect B. Okay, so we have this information, we have this information. What can we say about that information? We want to know something about this information. So one thing I could tell you is that 1 is greater than everything. 1, all these things, probabilities are, so this is 1 is greater than or equal to that. Okay, I don't know what B of AB, but one thing I can tell you is greater than or equal to that. Good. Now let's just plug in numbers. P of A, so we get 1 is greater than or equal to, probability of A is 0.6, plus probability of B is 0.7, minus probability of A intersect B. That's what we're looking for. We want to prove something about that. Okay, 0.6 plus 0.7 is 1 is greater than or equal to 1.3 minus probability of A intersect B. Okay. Okay, I'm going to bring this to this side. I'm going to bring this to that side. And so I get probability of A intersect B is greater than or equal to 1.3 minus 1, bring that to that side, which is equal to 0.3, which is exactly what we wanted to show. So we just use this formula to plug in, to find things. Okay, good. So that's number 8. Can we do number 10? I'm not going to do number 10 simply because you got to know poker for it. Now I do poker in the answer to section 5.1, but you know what, since I'm assuming you people didn't see that, and I'm assuming most of you probably don't know poker, so I'm going to skip number 10, but you can see it. At the end of section 5.1 there's a little introduction of what poker is all about, and what type of cards, what 5 cards poker is all about. But let's do number 12. Okay, number 12. 2 dice are tossed as an exercise 11. The main point is these 2 dice are different. One is a red dice, one is a blue dice. One is a green dice, one is a blue dice. One is a red and blue. I don't care what they are, but I can tell them different. We'll talk later on about how you can talk about other types of when they're both white dice and you can't tell them apart. Okay, so let's read the number 12. 2 dice are tossed. What is the probability that the maximum number on the dice is 4? So let's just go through. If you have 2 different dice, here's what the state space looks like. Well, let's see, what can I get? I can get a 1 and a 1. I can get a 1 and a 2. I can get a 1 and a 3. I can get a 1 and a 4. I can get a 1 and a 5. I can get a 1 and a 6. I can get a 2 and a 1. I can get a 2 and a 2. Okay, I'm going to have 1, 2, 3, 4, 5, 6. I'm going to go all the way down to, I can get a 6 and a 1. I can get a 6 and a 6. Okay, so the number of elements in my state space is 36. There's 6 possibilities for the first one, 6 possibilities for the second one. Simple as it can be. We'll talk later on about what happens when they're the same. Good. Now let's do 12a. I want to know what's the probability that the maximum number of the die is 4. Okay, so I'll tell you what that is. On the bottom, I'm going to have 36. On the top, which die, when I throw them, 2 of the die, the maximum number is 4. Okay, and the answer is, let's see, 1, 4, 4, 1. 2, 4, 4, 2. 3, 4, 4, 3. 4, 4. Okay? Can't do it any other way. 1, 2, 3, 4, 5, 6, 7. So this is equal to 7 over 36. Okay? Let's do 12b. 12b. The minimum of the numbers on the die is 4. Okay, so let's do this. So again, the bottom is 36. That's what we're going to have. And then the minimum number is 4. So it's going to be 4, 4. The minimum number there is 4. 4, 5. 5, 4. 6, 4. 4, 6. Can't think of any other ones. Okay, that is the minimum number is 4. 1, 2, 3, 4, 5. So this is equal to 5 over 36. Okay, 12C. The product of the numbers on the die is 4. This is 12C. The product of the numbers on the die is 4. So again, the bottom is 36. The product is 4. So think about it. What can give me 4? 1 times 4 is 4. 4 times 1 is 4. And 2 comma 2 is 4. So this is equal to 3 over 36. That's it. Great. Good. Now I want to talk about something else. This is not in the book, but I want to talk about what happens if the both die are the same color. I can't tell them apart. So then my state space is much smaller. Let me show you. Okay. I'm not, again, this problem is not done in the book, but we should just be aware of it. Okay? The state space is like this. I'm not going to use square brackets because I don't care about the order. I don't care what's first and what's second. Okay? Because I can't tell them apart. So watch what I can get. I can get 1 comma 1. I can get 1 comma 2. I can get 1 comma 3. I can get 1 comma 4. I can get 5. 1 comma 6. Now, 2 comma 1 is the same thing as 1 comma 2, so I'm not going to write that again. And I'm not going to write 1 comma 1 again because we have that already. So I'm going to write 2 comma 1. I'm not going to write 2 comma 1. I'm going to write 2 comma 3, 2 comma 4, 2 comma 5, 2 comma 6, 2. Okay, no more 2's. Great. Now what else? I'm going to write 3. Oh, I left out 2 comma 2. 2 comma 2. 3 comma 3. 3 comma 4. 3 comma 5. 3 comma 6. 4 comma 4. 4 comma 5. 4 comma 6, 5 comma 5, and 5 comma 6, and 6 comma 6. And hopefully that should give us 21. I think it's 21. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. There are 21 possibilities. Okay, now in some of these problems, you see 4, 1, 1, 4, 4, 1, that's going to collapse to one thing, 2, 2. So these two things are going to collapse to 1. And you can do the same problem for these dice that look exactly the same. I cannot distinguish these dice. Great. Okay, so that's problem number 12. Let's do number 14. Okay. Number 14 is a little bit of theory. It's not hard. Okay. It just says if E is a subset of F, then, this is number 14, then the probability of E is less than or equal to the probability of F. And this is very simple because just think about it this way. Here's your sample space. Here's E. Sorry. Here's F. Here's E. Look, how many elements are in this compared to this is less than how many elements are in this compared to this. So we write it as follows. This is the number of elements in E divided by the number of elements in this. We want to show that's less than the number of elements in F divided by the number of elements in the sample space. Well, these guys, there are fewer E's than F's, so it's done. And these are all finite sets, there's nothing to worry about. Great, number 16. sorry, a little bit theory. Okay, P of E. If P of E and P of F are, if they're equal to P of E intersect F, okay, and then E and F, F are called independent. Okay, so we need that. Great, let's do number 16. A fair coin is tossed until a head is obtained. What is the probability? I'm reading away from you. Number 16. A fair coin is tossed until a head is obtained. What is the probability that the coin was tossed at least 4 times? Okay, now we need to work on our English. What does it mean at least 4 times? Does it mean at least 4 times? Number 16. At least 4 times means 4 times, or 5 times, or 6 times, or 7 times. At least 4 times means 4 times, or 5 times, or 6 times, or 7 times, ... Let's just write it like this. P of at least 4 times means P of 4 times plus P of 5 times plus P of 6 times plus ... Okay, now there's a problem here. That's an infinite summation. That goes on forever. Don't like that. Okay? We don't like that. I don't know how to do that. Okay, but here's another way of doing it. Okay? What's the opposite of this? So this is really equal to 1 minus P of at most 3 times. In other words, if I want to do at least 4 times, that means I have to add up all of them. But how about if I say, look, it's not 3 or less. If it's not 3 or less, then it's 4, 5, 6, 7, or 8. Okay, again, not 3 or less means 4, 5, 6, 7, or 8. So now I have a much easier problem, easier thing. So I want to know what P1 minus, what does it mean at most 3? So that means 1 minus probability of 0 times. Let's use the word times. Plus probability of 1 times. Plus probability of 2 times. At most 3 plus probability of 3 times. Close parentheses. Okay. Now, if I say at least 4 times, let's just read the question again. Number 16. A fair coin is tossed until a head is obtained. What is the probability that the coin was tossed at least 4 times? Okay, so could be 4 times, 5 times, 6 times. Another way of saying is it was not tossed at most 3 times. That means it was tossed 0 times, 1 times, 2 times, 3 times. Okay, great. Okay, now this doesn't make sense. You can't toss it 0 times and not get a heads. What you could do is toss it 1 time and get a heads altogether. Okay, so let's read the question again. I'm sorry, we have to read it a few times. A fair coin is tossed until a head is obtained. Okay, what's the chances of it doing it one time? Well, you flip it the first time, you get a half. Great. The chance of getting a heads is the first time. 2 times. What does that mean? Well, first, so this is a heads. First time you got a tails, then you got a heads. So how is that possible? A half times a half. Great. 3 times. That means you got a tail the first time, a tail the second time, a heads the third time. So this is a half times a half times a half. Okay. So now we do this. 1 minus a half plus a quarter plus an eighth. Okay. Okay, let's just combine like this. So this is 1 minus 4/8 plus 2/8 plus 1/8, okay, which is equal to 1 minus 7/8. 4 plus 2 is 6 plus 1 is 7/8. Okay, which is equal to, this is 8/8 minus 7/8, this is 1/8. Finished. So, the chances of getting at least 4 times is 1/8. Okay, we use the not thing here, and we use the or because we're doing more than one thing. Okay, great. Number 18. I'll read it to you. Number 18. The probability of my winning the first game of backgammon is 0.5. The probability of winning my second game is 0.4. And of winning both games is 0.3. What is the probability that I will lose both games? Okay, great. Okay, so let's read that. Okay, so probability, this is number 18, probability of win 1 equals, let's read the question again. The probability of winning the first game, the probability of winning the first game is, don't move, 0.5, 0.5. Of winning the second game, probability of win second game is 0.4, 0.4. Great. And the probability of winning of both games, probability of win 1 and win 2 equals 0.3. Okay. What is the probability that I will lose both games? Okay. So probability of lose both. What does that mean? That means I do not win the first game or the second game. So this is the same thing as 1, lose both. Lose is a way of saying not win. So do not win. Probability of win 1 or win second. Okay, let's do this. This is equal to 1. We have the union rule for this. So this is 1 minus probability of win 1 plus probability of win 2. 1 second, I added them twice, so I have to do minus probability of win 1 intersect win 2. Close the big parentheses. Let's just say this again. Probability of losing both means I did not win the first one, or the second one, or both of them. I included that twice, so I have to erase that. Okay, the rest I just plug in numbers. This is 1 minus 0.5 plus 0.4. 1 second, we could do it once. Minus 0.3. So 0.5 plus 0.4 is 0.9, minus 0.9 is 0.6. So this is 1 minus 0.6, which is equal to 0.4. That's the final answer. Okay, great. Number 20. Okay, it's a nice problem. Again, you got to pick up the English. This is hard only because of the English. Okay, let's do number 20. Okay, let's read it. A student answers a 3-question true or false test at random. Let's just see. He has 3 questions. The first question you can answer true or false. The second question you can answer true or false. The third question you can answer true or false. Which means the student can answer, there's one of 8 possibilities of how they can answer these questions. Okay. They're answering it at random. A student answers a 3-question true or false test at random. What is the probability that she will get at least 2/3 of the questions correct? Okay, what does it mean 2/3? Okay, so the state space is 8. Let's write it 8 as 2 to the 3rd. Okay, because that's how many you can have. Now, what's the chances of getting at least 2/3 correct? That means 2 out of 3 correct, or 3 out of 3 correct. Okay, so the answer is as follows. Okay, the bottom has 2 to the 3rd. Okay, now you want to know which of those 2/3 are you going to get correct. So let me just say it like this. You have 3 questions. 2 of them you're going to get correct. That's one possibility. But there's another thing that's a possibility, namely 3 of them you can get correct. Because we're asking at least 2/3 correct. So you have this. Okay? Let me just tell you, this is equal to 3. There are 3 possibilities of choosing 2 correct ones. And this is equal to 1. So this is equal to 4/8, which is equal to 1/2. Okay? B and C is exactly the same question. It goes as follows. Repeat part A for a 6-question test. Okay? So repeat part A for a 6-question test. So this is, there are 2 to the 6 possible answers, and you want 2/3 correct. Let's see what's 2/3 correct. 2/3 of 6 is 4, but you want at least 2/3. So you want 4, 5, or 6. So the answer is, you have 6 questions, you want to choose 4 of them, or you have 6 questions, you want to choose 5 of them, or you have 6 questions, you want to choose 6 of them. This is 1, this is 6, I don't know what that is. Okay, let's do part C. Repeat it for 9 questions, so you have 2 to the 9, and you want to get 2/3 correct. What's 2/3 of 9 is 6. So you have at least 2/3. So you have 6 questions. I'm sorry. You have 9 questions. You want to get 6 right. Or you have 9 questions, and you want to get 7 right. Or you have 9 questions, and you want to get 8 right. Or you have 9 questions, and you want to get 9 right. And that's your answer. Okay? So let's just go through. We did all the even number problems. The homework asks you to do the odd number problems. I'm going to put up a video with all the odd numbers answered. I'm going to do it as quickly as we did this, but I strongly, strongly recommend that you try to do it on your own. Do the odd number questions on your own. Use me as an aid to see if you're correct. Have a wonderful night.